Hi guys, today we're learning about circles. We're just kind of doing an abbreviated version of it this year, so today and tomorrow we'll be talking about circles. So we're going to do the first half of these notes and then finish them tomorrow. So in order to get started, we have to do some vocab. The first vocab word that we're going to talk about, its definition is a segment whose endpoints lie on a circle, and that word is a chord. So chord by definition is a segment whose endpoint, so it's two endpoints that are on the circle. The next word, a line in a plane of a circle that intersects at exactly one point is called a tangent. So it is a line and it intersects at exactly one point on the circle. We're going to draw this in a second, that's why I've got it color coordinated. The point at which the line intersects the circle on this line is called the point of tangency. Point of tangency. So it's the exact point where the line is tangent. And then the last word, a line that intersects a circle in exactly 2 points is called a secant. So this is also a line, but it intersects at 2 points. So we're going to draw a big circle and we're going to do an example of this. So I don't have notability magic, so I'm sorry if this is not a great circle. Oh, not bad. Okay. So first I'm going to draw a chord. So it's a segment, so that means it ends, and it has two endpoints that lie on the circle. So we'll say one's here, and we'll say one is there. And so we're going to connect them. That straight line is called a chord. The next line that we're going to draw is a tangent. So we're going to have 1 point, and there's going to be a line that only touches the circle at 1 point. This one's kind of hard to draw, so be patient if it looks like it doesn't intersect or if it looks like it intersects at more than 1 point. So pretend that that line touches the circle at that 1 point that I have drawn. So that line is called the tangent. And then the point that it intersects at is called my point of tangency. So I'm just going to abbreviate that. PTTAN, point of tangency. And then the last one is a secant. So again, I'm going to have 2 points on the circle, but it's a line, so it goes all the way through. So I'm going to have maybe like a point over here and a point over here, and it's going to be the line that goes through it. And that's my secant. All right, so let's practice that. Okay, this exercise says tell whether, well, it should say tell. I don't know what's going on with the letters. Maybe it looks normal to you. Whatever. It says tell whether the line or segment is best described as a chord, a secant, a tangent, a diameter, or a radius of circle C. So the first one is HC. Okay, so the first one is HC. So if I go find HC on my picture, H is here, C is there. Ooh, come back. And the line that connects them is what we call, yep, a radius. It goes from the center to an edge or to a point on the circle. So that's not any of the new words we learned. That's a word we already know, radius. All right, next we'll do BE. BE goes from here to here, 2 endpoints, and it stops. We call that a chord. Very good. It's just a segment, it's not a line, so it doesn't go on and on forever, but it does go from one endpoint on the circle to another endpoint on the circle. All right, the next one is BH. I'm going to erase some of this just so we don't have to keep looking at those same colors. BH goes from B to H, goes all the way through. So it goes from one end of the circle to another. So by definition, that's a chord. But this is a special type of chord because it also goes through the center. And what do we call a line that goes right through the center and cuts the circle into 2 equal pieces? Yep, a diameter. So this one has 2 words that go with it. Okay, we got two more lines to look at, and these ones are actually lines because they've got little arrows at the end. So DG, it uses the points D and G to refer to it, but it's an arrow because it has a line because it has arrows at each side. I know that it uses 2 points to name it, but how many points are on the circle? 1E, which means that this is a tangent line. And then the last one is the line AF. Now, I know that AF is not drawn as a line on your paper, as in there are no arrows, but we can draw that for us. It goes through A and F, and it says it's an arrow, so it goes on and on forever on both sides. And this one is called a, yep, the last word, a secant, because it hits the circle twice. Secant. Cool. All right, now time for our favorite, always, sometimes, never. There's just 4 of them, okay? It's just going to help us think through them. A diameter is blank a chord. So if I have a diameter, is it always a chord, is it sometimes a chord, or is it never a chord? Well, by definition, a chord is a line that goes through both endpoints. So if I have a circle, both of its endpoints are on the circle somewhere, and a diameter is what I said is a special type of chord that just goes through the center. So this one, I'm going to say always. Okay. A radius is blank a chord. Now we know a radius goes from the center to the outside, and we know a chord has 2 endpoints on the circle. Is a radius always, sometimes, or never a chord? Yep, never. Never, ever a chord, just by definition. All right, next, a chord is blank a diameter. Ooh, it's like number 1, but we flipped the order. Does that change things? A chord is blank a diameter. So a chord just has endpoints that are on the circle somewhere. This is a chord I'm going to draw in blue. Is this also a diameter? No. Could I draw a chord that is a diameter? Yeah, I already drew one in black. So this one is just going to be a sometimes. And then last, a tangent is blank a secant. How many times does a tangent touch a circle or touch the endpoints of a circle? Yep, 1. How many times does a secant touch the endpoints of a circle? 2. Can you do those at the same time? Can you hit just one point and hit 2 at the same time? Nope. We're going to say never here as well. Tangents and secants are never the same. All right, keep moving. We got a couple theorems to talk about next. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. Okay, so we're going to look at this example. I've got a picture drawn for you over there on the right. If the line L is tangent to circle Q at P, so P is my point of tangency, right here at P, and L is tangent to the circle, which means it only hits once, then what 2 things are perpendicular? Line L and segment QP. Ooh, I did not write Q or P. There we go. Segment QP. So the radius QP and line L are perpendicular. So I'm going to draw a little perpendicular sign. Same thing if we went backwards. If we knew that those 2 were perpendicular, if we knew L and QP were perpendicular at point P, then we would know that L is tangent to circle Q. To do circle, we do a circle with a dot in the middle. I know that's ugly. Please ignore it. Or draw a prettier one on your paper. But if I know that this perpendicular thing is a true statement right there, then I know that L is tangent. So then I would be able to write tangent right there. Okay? We're going to use that concept in order to solve the problems on this next slide. Okay, so all of these give us that they are tangent, or it gives us perpendicular marks. So this first one says ED is tangent to circle O. What is the value of X? Well, if ED is tangent to circle O, then I know that I've got a right angle right here at angle D. That's helpful to me because now I'm able to make this little right triangle out of all the shapes and lines on my picture. That right triangle shows me that I have one angle that's 90, I have one that's 38 and I've got one that's x. And so we can find x by adding them up and setting them equal to, yep, 180. 90 plus 38 plus x equals 180. Add those up, subtract from 180, x equals 52. Awesome. Let's do the one below it. Is ML tangent to circle N at L? Explain. Ooh, we wonder, are they tangent? If they are tangent, then this would be perpendicular, right? So I'm kind of asking, is that angle at L a right angle? If it were, what would be true about all my sides? What old theorem could we use to help us figure out if L is a right angle? Yep, it's our favorite Pythagorean theorem. 7 squared plus 24 squared equals, does it? 25 squared. If they're both the same, then we'll say yes, it's tangent, yes, it's right, but we got to check it first. 7 squared is 49, 24 squared is 576, 25 squared is 625, 49 plus 576, oh, that is 625. 625 equals 625. That's good. So is this tangent? Yes. ML is tangent. Ooh, there we go. To circle N. Yay. All right, next, what is the radius of circle O? So I already actually labeled this picture for you, which is awesome. So we know that the radius goes from O to the sides of the circle, so I have two little segments labeled as X. We have one line that goes from the point of tangency to some point outside the circle, that's 10, and then we have a point that goes from O to a point outside the circle that includes the radius x and adds 6 more on. So that's important that we know that those are being added up together. In this case, my hypotenuse is going to be right here, and we're going to do Pythagorean theorem again, but this segment right there, that's going to be your C side. So I've got x squared plus 10 squared. Again, it doesn't matter what's a and b as long as they're both on their own side. But then c is not just going to be x squared or 6 squared, it's going to be x plus 6 squared. Now this is a mistake even my seniors make sometimes, so if you make this, it's okay, but we got to work to not make it. We forget sometimes that we have to FOIL out x plus 6 squared. It's not just x squared plus 36. You have to think of it as x plus 6 times x plus 6. So you got to FOIL that. X times x plus x times 6, and then 6 times x plus 6 times 6. That gives us x squared plus 6x plus 6x plus 36, which gives me x squared plus 12x plus 36. If you don't FOIL, then you lose your middle term, and then we will have an issue. So please, 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 please remember to FOIL. Okay, so my other side is 10 plus 100, because those were two separate numbers squared. And then my right side is x squared plus 12x plus 36. And we got to get like terms. Oh, I lost my square there. Okay, we're good. So I'm going to minus x squared from both sides. Well, those cancel out. And then the only other thing I combine are my constants. So if I minus 36 to take it to the other side, that's going to give me 64 equals 12x. And then I can divide that by 12, and that gives me, I have in my notes 16 over 3. I don't know what that is in the calculator, so if you put that in the calculator and you get an answer, like if you do 64 divided by 12 and get an answer, check and see if that's the same thing as 16 divided by 3, because they should be the same. And so that's what your radius, that's what x is in this picture. All right, last one of this type. It says ML and MN are tangent. That means if they're tangent at the points of L and N, which means that we've got some right angles in here. We've got a right angle at N, and we've got one at L. I can find X pretty easily, because what should all the angles in a four-sided figure add up to be? Yep, 360. So I'm going to do 90 plus 90 plus x plus 117 equals 360. I'm going to add up all my numbers, my constants. I get 297 plus x equals 360. I'm minus 297, and I get x equals 63. Oh, awesome. End of the first page. Keep rolling. We got a half side left. We got one more theorem that we're going to do today, and then a couple examples. So this one we call an ice cream cone theorem because it kind of looks like an ice cream cone. Now that spring's coming, it's almost ice cream season. Who am I kidding? We eat ice cream all the time, don't we? Okay, it's like an ice cream cone. The little circles like your ice cream scoop, and then the segments RS and ST make what look like a cone. So if 2 points from the same exterior point, so in this case that same exterior point is S, if they are both tangent to the circle, then they are congruent. So if they come from the same point S and point R and T are both tangent to the circle, then we know that their segments are the same. That means that RS is congruent to TS. So it's from S to T and from S to R. So those segments would be congruent. There we go. All right. Okay, so let's do a couple examples using that concept. So O is inscribed. We'll talk about inscribed in a little bit. It means it's just inside of this triangle shape PQR, and the triangle has a perimeter of 88 centimeters. What is the length of QY? So we're trying to find this length right here, and we know that we've got a perimeter of 88. If it's perimeter, we just add up all the pieces. So we can do 88 is equal to all the pieces we have. But I only see two numbers out here, so we got to do some common sense or some knowledge from our theorem in order to go on from here. Based on our theorem, if they come from the same exterior point and are tangent, then we're able to say that they're congruent. So like XP is congruent to ZP because they're both tangent and P is a common exterior point. So I'm going to call this also 15. So I can say 88 is going to be 15 plus 15. It's obviously more than that, but those two are good right now. And then over here, ZR is 17. Well, YR is also 17 because they come from the same exterior point of R, and Z and Y are both tangent to the shape. So I'm going to say plus 17 plus 17. The only thing is we don't know what QY is, and that means we also don't know what XQ is. But those have to be the same, so we're just going to call them X or something, and so we'll say plus X plus X. Now we're going to combine like terms and then subtract in order to solve. So I have 88 equals 15 plus 15 plus 17 plus 17. And then plus x plus x. So 15 plus 15 is 30. 30 plus 17 is 64. Plus 2x minus 64 from both sides. And then I'm going to divide by 2. So x should equal 12. And that's how long QY is. So you could label it X or you could label it QY. Okay, two more examples. Again, these are all the same concept. So this next one looks like a different shape, but it's already labeled and we're going to use our same concept as before. So quadrilateral RST is circumscribed about. That means it's on the outside of circle J. If its perimeter is 18, we're going to find X. Okay, well, let's label everything. It looks like AS is 3, and so that means SD is also 3. It says DR is 3, so that means that CR is also 3. It says UC is X, so that means that BU is also X. And then it says TA is X, so I'm going to say TB is also X. So this is nice. We got a lot of the same numbers. My perimeter is 18, so 18 equals all of these things added together. 1, 2, 3, 4, 3. So I'm going to say 4 times 3. And then 1, 2, 3, 4 x's. So I'm going to say 4x. You could write out all your 3's and all your x's, but I just don't feel like doing that today. So I've got 3 times 4 is 12. 18 minus 12 is going to be 6. 6 equals 4x. and then divide by 4, x is going to equal 3 over 2, or about 1.5. Oh, excuse me, about 1.5. So whichever answer is fine. We don't have a unit, so you can write units behind it, but that's as exact as we're going to get with that one. Okay, and last one. Threw a little bit of a curveball in this one. It says AB is tangent to C, or circle C at point B, and AD is tangent to circle C at point D. Find the value of x. If they're both tangent, we know that those are the same. So I'm going to set them equal to each other. X squared plus 24 equals 49. Ooh, I got a little square here. That's going to cause some things, I guess. First thing we'll do is get x squared by itself. So I get x squared equals minus 24 from both sides, and that gives me 25. And then I get to square root both sides. So x equals 5. Now, we can't just leave it at 5, because if I were to plug this back in, 5 squared plus 24, yes, that is 49. Is there another number I could also plug in, though, and square and add that to 24 and also get 49? The answer is yes. We actually have to do plus or minus 5 here, since it's using x squared. If it was just an x, it might be different because it could maybe not give us the same number, but since it's only x squared, either number you plug in will give you the correct answer. So there are 2 answers here. So make sure that you have 2 answers. All right? Well, that's day 1 on circles. Reach out if you need anything, and good luck practicing it.